take a relatively common or basic data set like the iris data set, and we collapsed it so that it was just one. I think it's Virginica, which is is the gray, and red is other flowers, and then you try to build a classifier to say if it's on. I give you one of these things and which one is it, and they don't tell you what the label is. So the basic classifying problem, is that clear to everybody? Everybody knows what a classifier is. And if it's a linear classifier, it's going to draw a line in your feature space. And this just has two, the length and the, actually what is that? Sepal length and width. And as you can see, this is pretty good, pretty separable. But you're going to have some problems. You're going to have some false positives. And you're usually concerned with just one class and not the others. And often the data set is very skewed. This one isn't. It's got about an equal number on each side. But we'll talk about a little bit in a second. So what you do if it's really skewed. So this is a little skewed. You can see I guess it's actually 1/3, 2/3. You can see that here. And we trained a random forest, and we used a cross-validation. And I'm assuming everybody knows what cross-validation is. Is that true? Does everybody know what a cross? Should I real quick? Okay, I will. So the basic problem with any kind of classifier regressions is that if you test on your training set, you'll overestimate the accuracy of your model. And so one thing you need to do is make sure that you're testing on something that you didn't train on. So one way to do that is to take your data set and sort of break it into pieces and say this is going to be training and this is going to be testing. And that's fine, but one of the problems with that is that this, first of all, you don't get as much training data, and second of all, you don't get as much test data. So how confident you are in this number that you get out of here is not going to be as high as if this was bigger. So maybe you decide to go like that, but now you're not training on very much, so maybe you're underestimating because if you had more training data. So one way of getting around this problem is to break up your data set into some number, often 10, but it doesn't have to be. And what you do is you train on this part, test on this part, and then train on this part, test on that part, and then you get the idea. So you basically end up testing on all parts of your data set, but always in a not having seen it before mode. And then you just aggregate up the accuracies. You can either do it in a micro or a macro averaging kind of way. So that's called cross-validation. Okay. So we did that there, and in addition, actually, and Jay and I we're not. Go ahead.
You mean Karen with the E, right? Just in case someone's looking it up.
I'm sorry. Yeah, that was probably that's what happens when you do this late at night. But and I'm interested to find out the other things that happen because I actually haven't looked at it since I put it together. So the other thing we did is we bootstrapped, and actually in this train control, and I don't use Carrot all that often. I usually just use Bear, and we had a roll your own cross-validation method that we used. But the number 10 I assume is how many folds, so that's the number of pieces of pie. And the repeats is you bootstrap bootstrap the data set. So you pick from the data. So if you have 100 things and you're bootstrapping you pick 100 from that with putting the things back. So you might have the same thing a number of times. So you're going to create 5 data sets with bootstrapping and then cross-validate on each. And I actually don't know how this works. Either on each of them, maybe make one big giant one. I'm actually not sure how that works. Do you know, Jay?
Splits.
I'm sorry?
It's 5 different splits. So you split randomly.
Mm-hmm.
Do the 10-fold cross-validation.
Okay.
Okay. go through that tenfold, and then you erase your splits.
Okay,
Put another set of random splits in.
okay,
And that, what they're trying to do is get around the, you just happen to put
Yeah.
all different points into one of your
Right.
splits just randomly.
hmm
Um,
So you either do really well, you either do really well or really poorly, depending on how.
It just is a random function of having split it a certain
Right.
way, and so that's why you do
Right.
multiple repeats.
So you're basically trying to make your results. So if you were to do this over and over again with different seeds, you'd get pretty much the same accuracy number, regardless of how you. So you're reducing your variance essentially on your experiment, on the estimate of your accuracy of your system. Okay.
So how is that again? You have your data, and that number 10 means you take 1/10 out and you store it away for later.
Well, yes, right.
And then you were talking about randomly. Okay, so you've done that.
Well, no, but you do that 10.
Put it back and take another 10th out somewhere.
Well, you split it into you take the cross validation is you split it into 10 pieces. You train on 9, test on 1. Train on a different 9, test on 1. Train on a different 9, test on it. Do that 10 times. So that's the standard cross validation.
And the only result is the error from that. You don't have those actual pieces and parts aren't available to, well, they're kind of available to you, but you don't use them for any particular purpose. Just the real result is what's the error rate coming out of that.
But when you do this with the bootstrapping method, you in addition, well, either bootstrap the actual data set, or I think what you were saying was you actually split you pick different folds each time.
That's my understanding.
Yeah.
Okay.
So it's another thing layered on top or actually underneath to.
So it's you do that 10 times or you do that 50 times.
You would be training 50 models,
Okay.
right? And then testing on a tenth of the data. Yeah. There's different ways of doing this, and there's actually papers on well, why not 4 instead of 10? Why not 20 instead of 10? Why not just 1 and all the rest? Leave 1 out. And there's different papers on what makes the most sense. So, okay. And I think one thing is when you do an evaluation is what's your baseline? Like how hard is this problem? And so for example, one thing is just to pick the majority class. So first of all, what's your metric? So one common metric would just be accuracy, which is if I have 10 things that I have to classify, what percentage did I get correct? So if I get 2 out of 10, I got 20%. If I got 8, I got 80%. So what's a baseline? And a reasonable baseline is just to pick the majority class. So here it would be, since it's 1/3, 2/3, you're going to get 66% correct if you just always pick, not Virginica. So that's a common baseline. And like I said, the accuracy is just how many you get correct divided by the test population. And kappa is a little different. Kappa is of the remaining bit that you have from your majority class, let's say your baseline, so 66%, of that proportion that's left over from the 66%, which is 44, how much do you get of that? So if I have a classifier and it gets, let's see if we can get some numbers that are round, and it gets 77%. It's essentially getting 1/4 of the remaining parts that it could get right over and above the baseline. So it's going to get 0.25 kappa. So does that make sense? So you're just saying, look, I don't care if you get, and so if your baseline, let's say, is 90%, and you say, I got an accuracy of 95, it's like, yeah, well, that's great. I mean, the baseline is 90. It's just not a hard problem. So kappa gets rid of that. So that's nice. So so again, that's one thing to really pay attention to. And the more skewed the data is, the easier the task is if you look at it purely through the view of accuracy by itself. where accuracy is just how many correct. Okay, so if the data is very skewed, as I mentioned, kappa will express that to you. But is there something different than kappa? Can we do anything with the different runs that fall out? Yeah, this is another thing that the obvious thing, I think, if you think about this, I've got these different runs, and so I'm getting different accuracy numbers, and they're bouncing around some mean. So you would think I can do some kind of confidence interval with the different runs that comes out of here, and we'll see that. So that's essentially the basic idea. All right. So do people know true positive, true negative, false negative? The basic idea is if you have, let's say, truth and system, if this is yes, no, yes, no, this is a true positive, this is a false positive, this is a false negative, and this is a true negative. Is that clear? And then most of your, I think I even say all of your classification metrics are just different ratios of these things. And so, so accuracy is just this one and this one over the sum of all of them. And there's many different ones. So precision is yeah, sensitivity, specificity, and false positive rate, but precision. So I come from the natural language processing information retrieval world, and the words they use, the ones they like the most, are precision and recall. And so that's what I'm going to discuss. But there are lots of other ones. If you come from the medical world, specificity and sensitivity are usually what are used. And there's pros and cons to these. But I'm just going to stick with this one. So precision is essentially, if you guess, and the other thing I have to say is for these you have to pick what class matters to you. So you have to say, okay, what I care about is whether or not I find a Virginica. And I don't care about not finding that. So I'm focused on Virginica. I want to know how often I find those. And so I'm allowed to not guess, basically, is one of the things. Is if I say, I don't know, I'm not sure this is a Virginica, I'm going to punt on it. So if you look at it that way, then precision is, of the times that I guess, which is going to be the denominator, how many do I get right? What's the ratio of how many I get right over how many times I guess? So it's basically, it's the probability, I can hope I get this right, of, so precision is the probability of, let's see, how to write this. Well, first of all, I shouldn't do it on an angle. Now, let's see, that equals. So it's given that I say it's that it is. So I'm going to go like that. P of, given that it's that the system says it's, I'll say Virginica, V. How often does the truth V? So how often is it right? Given that I said that. So that's your denominator. Okay? So that's one thing, that's precision. And then recall is same numerator, the ones I get right, over how many there are altogether in the data set. So how many Virginicas there actually are, which is the true positives plus the false negatives. It's a little weird of saying it. This is basically, you look at the whole population, how many of that flower type are there? So it's essentially how many did I find? So these trade off one another because one is how often I guess. And one way, how can you make, you can make precision probably pretty high if you only guess when you're really sure. So most classifiers spit out some number between something, 0 and 1 often, but negative infinity and positive infinity or something. And if you just say, I'm only going to go when it's above 0.9, then your precision will be high, probably, and your recall will be low, because you won't find very many. But you can make recall 100 by just saying everything's a Virginica. I'll find them all. But my precision will be awful. So that's the trade-off. And often, if you're working with people, they can tell you sort of how important which ones are. So if you're working, let's see, what's a recent example? I'd say like with information retrieval, if you talk to lawyers and you say, do you care if I miss one of the cases that's relevant, one of the decisions that's relevant to your case? They'll say, yeah, I care a lot. Recall better be high. And then you say, do you care if you have to go through a lot of things that are actually false positives, documents that are not relevant? And they say, that's okay. I'm willing to go through a lot of those if you can really make it very unlikely that I miss a case that's relevant. That's very different from someone who's looking for, let's say, cameras. And they're interested in reviews of cameras. Let's say they're interested in, and you say, you're willing to look through a lot of different reviews that are awful. And they have nothing, they're not even reviews. They're just like have nothing to do with the camera. And they'll say, no, I just want a couple good reviews at the top, and I'm willing to miss all kinds of reviews because they're probably the same. So that's someone who really is interested in precision and doesn't care about recall. So when you're building a classifier, you need to talk to, if you're not building it for yourself, if you're building it for someone else, then you better go ask them which one is more important. Okay. So that's one of the trade-offs. And you can see this in medical stuff, obviously. If you're doing a test for whether or not someone has AIDS, you're going to want to be sort of clear about how important it is that you catch it versus all kinds of false positives, which also have a big negative effect, obviously. So you need to sort of figure out how that works. OK, so what does ROCR do? ROCR, R-O-C-R, what it does is it makes it very easy to calculate all these different measures. And it essentially, you can write this code by hand, and I've written it many, many times. And it's easy to get it slightly wrong, and that's very bad. So I would suggest that you consider using one of these things. So anyways, you just put in your scores and your labels on predict, and it essentially creates a data structure that saves up all these things. And then you use performance, and you say, I want precision and recall. Or then there's another ones. You can do sensitivity and specificity. And there's a whole slew of them. And then you give it overloads plot, and you give it one of these performance models, and it makes really nice pictures. And it does some other stuff. So that's essentially what I'm trying to. So in addition to telling you some stuff about how you do an evaluation, I wanted to let you know about this kind of cool package that makes it pretty easy to do these things. So this is a precision recall curve. Now one question you might have is, how come it's a curve? Why not it's just a point? Because you'd say, well, you have a classifier, it should just give me a precision and a recall. But as I mentioned, depending on where you put the threshold for guessing which one or the other. So it's going to spit out some number between 0 and 1. And you can tell, often it'll just always make it 0.5. It'll have some predefined thing. But if you say, no, I want the probability to be spit out, or some number, and random forest will do that. Otherwise, it'll just give you one or the other when you do predict. But if you train the model to say keep the probabilities, then it'll spit out a probability between 0 and 1, something that acts like a probability. And then you threshold it, and that's where you get your curves. So over here, the color, and actually we put the numbers on there, it's kind of small, is at a threshold of 0.4, we have this trade-off between recall and precision. At a threshold of 0.6, we have a different trade-off. And then up here, 0.9, so this is what I was saying. If you make it very stringent on when it guesses that it's a Virginica, then it has a high precision, higher precision. That's not terribly high, but higher. And then but the recall is a bit lower. And then as you start to let everything in, call everything a Virginica, your recall gets very high and your precision goes down. Yes.
So sorry, are the numbers along the line, are those accuracy then?
No, they're precision and recall. So accuracy, they're this numbers, these two numbers here. Accuracy is,
The numbers on the actual curve.
The numbers on the curve?
no, those are the that's the threshold. Yeah, they're not really, because you have the color, they're not actually necessary because you've got red is a threshold of 1. So it's saying you have a classifier. You don't actually change the classifier. What the classifier does is it spits out a number between 0 and 1 for every single thing you hand it. You give it, a you give it this flower, and it says 0.7. And you give it some other flower, and it says 0.2. And you give it some other flower. Okay, it does that. And it does that for your whole test set. Of course, you do it in a cross-validation way. So now you have these numbers between 0 and 1 for every single element in your test set. And now the question is, depending on what threshold I set, what's going to be my number of true positives, false positives, true negatives, true false positives. Is that clear? It's a good question. It's not entirely clear, but then what you do is you ask the people, whoever's using it, what is the trade-off that you want between these two numbers? How often you're wrong when you guess that it's a Virginica, and how many Virginicas you miss. And if they tell you I'm comfortable with with a threshold of 0.6 and 0.5, then you say, okay, the threshold is 0.7.
So it's the threshold at which you would classify something as, the probability threshold at which you classify something as Virginica?
Right.
Okay.
Yes.
Something that's
Okay.
surprising is that curve doesn't look monotonically decreasing.
Yeah. So it actually looks. I think it actually is, but it's not. It definitely can bounce around, and that's. So let's see. Why would that be? And that can be.
Or is that actually
No. I mean, no. It's not. No, it's not a problem. It can happen because you can have. Let's say. I don't want to take up too much time, but it can actually happen that when you let in a couple more, at a lower, it actually changes the trade-off. No, I don't think so. I think it's just that with your data set can be, but I could be wrong. I don't think I'm going to be able to think through it in front of everybody. So I'm going to punt on it. So one thing I wanted to mention, I sort of foreshadowed early on, was what can we do with the fact that we're actually running this many, many times? And so you're really getting many, many, many precision recall trade-offs. So what you can do is you can talk about what is my confidence interval around every single point on the graph. And so ROCR does that for you too. So you can imagine writing that code. It'd be a real pain, but that's I think a really nice thing and one thing that usually happens is it starts getting bigger and bigger over here. Well, at least let's put it this way: as we go over here, our precision number is based on less and less. So precision, remember, is of the things I guessed to be Virginica. So that's the bottom. How many are correct? Now, if I'm only guessing 5. That means that I get 2 correct. That means 2 out of 5. That's an extremely small number. And that's exactly what happens over here. Because these are the things that where you're forcing the threshold to be very high. On the flip side, right, so so that what should be happening is it should be bouncing around a lot more over here, essentially. And so you see that. So you shouldn't believe your precision numbers over here, basically, as much as the ones that are in sort of the middle. So, okay. So
that curve is smoother than the previous one. That's because you're averaging over several tests?
yeah, why was that, Jay? I don't remember. We fiddled around. I don't know. Again.
We'll make the code available so you can.
Yeah. Okay. So here's the lead into Jay's part. So we can go. So we're not here, all right. What if I wanted? So I took all this stuff and, of course, cut and pasted into Google Slides. And now, if I want to change anything because something was wrong, or I got a new data set. How do I do that? Well, right now what I have to do is I got to go back to the R, I got to fiddle with it, and then I generate stuff, probably drop it into a file, and then I take into different directories, and then I take this out and try to remember how I named the last thing, pull it in, and I do all this dragging and dropping in order to rerun my code, basically. And that makes the reproducibility of it. And in addition, questions like that. Like I might not, that's actually, thank you very much for leading into that. I didn't even realize. I can't tell you because I don't know, this is just this piece of, this image that's just sitting here. I don't have any link between this and the code. So, especially if I name everything the same, there's no way to get back to it. So I can't even ask that question. First of all, I can't answer what happened, and second of all, if I want to make any modifications, it's very arduous. So Jay's now going to tell you how to get out of that problem.
I don't want to leave your segue, but can I ask a quick question? If you're not predicting a binary outcome, the ROCR package, do you pick the class if you're doing your true positive line?
If you're not picking,
If you're predicting
multiple, if you've got 5.
so you got to pick a class.
Yeah.
If you're gonna base your true
I don't
positive
think
line.
so, but I'm not sure. I'm not sure.
You mean like, can you do multi-class
Yeah.
with ROCR?
Classification,
I mean,
yeah.
So you can do a ROCR, but you have to say which one you're predicting. or
Right.
To base your true positives on.
Yep,
So
I assume you can.
but this
Yeah.
ROCR package does not. It's only binary classification.
only binary.
Yeah.
Of course, you can fit it into that by wrapping your classifier and, yeah. Yeah.
That's my-
And one more quick question. Is there sort of a number of individuals or a minimum amount of data before you can just kind of walk into this world? Are we talking N of 100, N of 50? I mean, you obviously work with data sets that are.
Well, this is actually pretty small. You saw that was, what was it, 50 and 100. Of course, the main thing is the cursive dimensionality. You can't use very many dimensions.
Right.
Well, what you'll see is if you do cross-validation and stuff, you won't get. So you'll be in the world. You'll just realize that you won't be able to do very well because you'll overfit, and then you'll do terribly on the. So you need to do something. You need to reduce your dimensions, or you need to you have to regularize. If somehow tell the classifier don't try to get everything right. Yeah.
But the confidence intervals, like you address whether you have enough data.
Right.
You choose between one threshold and another.
Yeah, but you might still have a large confidence interval and still be able to. It might be enough for you, so that you can you still get something useful. It might be a model that you don't know exactly how it's going to do, but it gets somewhere between 60 and 80%. But that might be okay. So, but yeah, the confidence intervals will help you somewhat.
Any other questions for Mark? Thanks, Mark.